atoms, ions. So let's get started by looking at some things you already learned in chemistry. So let's just kind of do a quick review to make sure those concepts are fresh in your mind. And with that, we're going to start with atomic structure. So when we're talking about atoms and elements, we have to go back to that term matter. What is matter? Matter is anything that has mass and volume, and it's made up of more elements. So mass technically has a scientific chemistry meaning, but for us, let's just say weight, because we're not a chemistry class. Okay, so let's just make it weight. So anything that has a weight and has volume is mass, and mass is made up of elements. And elements are those things that you see in the periodic table of elements that you've seen in every chemistry classroom that you've ever been in. And there's almost 120 something of those, and they're arranged in tables and in rows, and those are important as far as what's going on with their elements, but not important as for this class. In other words, we're not going to be using the periodic table in physiology. But what is important about elements is they cannot be broken down into smaller individual chemicals. Now, the difference between an element and an atom is that the atom is the smallest unit of an element, and so it still has the characteristics of that element. And when you were in school, you learned about atoms having subatomic particles. All that means is particles that are smaller than the atom itself. And so we've known for years all about protons, neutrons, and electrons, and you learned all about that. If you took any college level physio class, you also probably learned about quarks and neutrinos and Boson-Higgs particles. For this class, we're just going to be sticking with protons, neutrons, and electrons. So to refresh your memory, the protons are the ones that have the positive charge. The neutrons are the ones that are neutrally charged. And both protons and neutrons are located in the nucleus of the atom. And then outside of them are the negatively charged electrons. When we look at those 118 different elements, there's only 25 of them that we require for life to occur. And I'm not going to have you learn all 25. Let's start with the big four. If you look at this picture, you can see that those four elements make up 96% of your body, and over half of your body is made up of oxygen. And then significant portions thereafter are made up of carbon and hydrogen. Well, you already knew your body was 2/3 water, so there's your hydrogen and your oxygen right there. Okay, and then carbon is the other biggie. And then equally as important is nitrogen, because nitrogen is what is required for all of your proteins. Okay. So those are the big four that everybody should know, and we need them for all 12 of our organ systems. Now, after that 96%, the next 4%, in other words, almost everything else, are going to be 7 elements, of which I'm sure you've already heard. For instance, you already know about calcium and phosphorus in your bone. Those are biggies. And then the next 3 are going to be salt, so either sodium chloride or potassium chloride. Okay. And so there's nothing there that you haven't heard before. And then if you add the 7 plus the 4, that's 11, which means then we have 25 minus 11, there's 14 more, and those make up 0.1% of your body, which means when we need to talk about them, we will mention them. But until then, just let them sit by the wayside. So if you take in nutrition, you probably have already learned about magnesium and its importance, but otherwise, until we come to talk about these other trace elements, we're just not going to mention them. But we are going to spend a lot of time today talking about oxygen, carbon, hydrogen, and nitrogen, because this is where a lot of our chemicals are made from. So moving away from atoms and putting them together, we can make molecules and compounds. And these terms technically are not the same. A molecule is any particle that has two or more atoms. Okay, and those atoms are going to be held together by chemical bonds, which we're going to learn about really soon. Okay, and so this picture is showing you two of the same type of atoms being held together. For instance, O2, oxygen. This is the oxygen we breathe. Now, we also can have two or more different atoms put together. So nitrogen oxide is one nitrogen with one oxygen, or water is two hydrogens with one oxygen. And carbon dioxide, dioxide is two oxygens with one carbon. And so when we look at these definitions and try to figure out what the difference between what you understand is all compounds, because they contain two or more atoms, are molecules, but not all molecules are going to be compounds. Now, as far as this course goes, you can kind of use the words interchangeably, because we're going to be talking about specific molecules or specific compounds. And it's safer just to use the word molecule, because that way you know the wordage is correct. All right. So now this is what I would like you to do. This is like, just pretend you went to Baskin Robbins or whichever place you want, and you had ice creams. And over on the left, you have a triple dip ice cream cone. All three look like there's strawberry in the middle. Somebody got a whole bunch of different flavors. The next thing over to the right is what you see on the wall, and these are today's flavor. And on the far right is the one scoop of what's like strawberry as well. So what I'd like you to do is stop this video and decide what each of these four things are representing of the terminology we've just discussed as far as elements, atoms, molecules, and compounds. So kind of figure that out. And do not continue until you have worked through this on your own. Just make sure your understanding is where it needs to be. Okay, so welcome back. And I really do hope you stopped and do that. Let's move on to those subatomic particles we mentioned earlier. So to refresh your memory, there is a neutron, which it has no charge. It's fairly big, so it has a pretty significant mass. The proton, which is also big with a significant mass, but it is positively charged. Those two are going to be in the nucleus. And then the electrons, which as you can see from the picture, are really, really tiny. They have a mass, but it's in the decimal points compared to the single digits of the neutrons and protons. And the electrons have a negative charge. And I'm sure in chemistry class, you've heard about two different models, the Bohr model, which was known as the orbit model, which is what a lot of people understand, with the nucleus in the middle. And then we have rings or orbits going around them, and the electrons are sitting in the rings. And just think of them like little traffic circles or whatever. It's very outdated, it's very inaccurate, but it's very easy to visualize and understand. And that actually is what we're going to be using for this class. The real model is the electron cloud, where we have the nucleus surrounded by this big amorphous clouds, and the electrons are going to be found out in these clouds. But what they both have is a symbolic representation of what an atom looks like, with a nucleus, with the neutron and proton, and then the electrons on the outside. But one thing that students often don't get is there is so much empty space in an atom. So if you stop and think for a second about the Coliseum in downtown Los Angeles, whenever USC plays football there, there's going to be the Trojan that's going to go right to the middle of the 50-yard line and take his sword and stab it in the ground. So assume that that part is the nucleus. So what I want you to do is stop and think, and stop the video so that you have time to think about that. If in the middle of the 50-yard line, that's where the protons and neutrons are, where would the closest electron be located? Would it be on the field, like where the players are? Would it be on the sidelines where the coaches are? Would it be up in the stands in the rich seats, or would it be up in the nosebleed seats, or would it be like at food services, or would it be in the parking lots, or would it be way out on the nearest highway? Where would that closest electron be located? And so I'm not going to give you the answer to that, but please feel free to ask me when we meet for class. So next time we meet up, and give me your answer, and I'll give you an idea so you can kind of understand what I mean by space within an atom. So let's look at this orbital model in the bottom right-hand corner, because this is the model that we're going to be used. So in the nucleus, you have your protons and your neutrons. And then we are going to have increasing diameter orbits around it. The closest orbit to the nucleus can only hold 2 neutrons. That shell is full once there are 2 neutrons in it. The next shell, or in other words, the second shell, can hold 8 electrons. And the third shell can also hold 8 electrons. Now, there are more. In this model, there are more shells, but we're never going to go beyond the third shell. So I'm going to stop with that. So in other words, if the innermost orbit was full, that atom would have 2 electrons. If the innermost and the second one was full, that atom would have 10 electrons, because it would have 2 in the innermost and 8 in the second one. And if 3 rings were full, it would have 18. 2 plus 8 plus 8. So hopefully you understood that math. So why is this important? Because when we look at these elements and atoms, they have what we call atomic numbers and atomic mass. So let's briefly review the difference between them. The atomic number is just the number of proteins that are found in the nucleus. So when you look at what's printed in the periodic table, you will have the element name, and on the upper, usually upper left, it will have a number, and that's the atomic number. So when we look at hydrogen, at the top of the square, it says the atomic number is 1. So that means it has 1 proton. As opposed to helium, which is on the far right, the first row of the periodic table, its atomic number is 2. So how many protons does it have? That's right, it has 2 protons. Okay. So what this means is, in an atom with no charge, a neutral atom, and that's how they are in the periodic table, the number of protons, in other words, the number of positively charged particles, will be the same as the number of negatively charged particles. Does that make sense? So the only way it could be neutral is if the pluses and the minuses add up and cancel each other out. So if you are told helium is a neutral particle, and you know its atomic number is 2, and you know that means it has 2 protons, then you know how many electrons it has. It's going to have 2 electrons if it's not charged. Now, if it does have a charge, we will come back and revisit how you calculate that shortly. But hopefully this is all reviewed. Now, the other thing besides the atomic number is the atomic mass. And once again, I said for our purposes, mass is weight. And the way the mass is calculated is it's the total number of protons plus the number of neutrons. Okay. So number of neutrons plus number of protons give us the mass. Now remember, the atomic number was the number of, do you remember that? Yes, it was the number of protons already. So if we are looking for protons and neutrons, and if we know the atomic number of carbon, the atomic number is 6, and the atomic number mass is 12, then we would say 6 plus what equals 12, and that would be 6. So carbon would have 6 neutrons and 6 protons, sorry. So you can see that the atomic mass isn't exactly 12. That's because there's some electrons in there that have a little bit of weight. Okay, so there's other subatomic particles that add to the weight. but we are just going to stick with numbers that are before the decimal point. We don't care about what's going on after the decimal point. All right, so looking at carbon, we know there are 6 protons because that's the atomic number. We know the atomic mass is 12, and we know 6 plus 6 equals 12. So that tells us there are 6 neutrons. Now, if you look at them in the shells, we know the first shell has 2 neutrons, sorry, has 2 electrons. So if this is not a charged thing, and we know we have 6 protons, then we know we have to have 6 electrons. So if we put 2 in the first shell, that means the second shell is going to have 4 electrons. In other words, it's still going to have 4 empty spaces where electrons could come and join. So that second shell is not complete. Continuing on, try looking at nobelium with an atomic number of 102 and an atomic mass at 259. Pause this really quick and figure out how many protons are there and how many neutrons are there. And if this was a neutral element, how many electrons would there be? And I'm not going to ask you to bring up among the shells because, like I said, we're only going up to 18 electrons, and nobelium has a lot more than that. So now let's talk about isotopes. We use isotopes a lot in the medical field when people are going and getting tests of like thyroid function or looking at bony structures, or even if we're carbon-14 dating how old something is, that is an isotope we look at. And what an isotope is compared to the element with its, on the periodic table with its atomic number and its atomic mass. An isotope changes the number of neutrons, which means the atomic number has stayed the same, but the atomic weight, mass has changed. Okay? So all the atoms of the element are going to have the same atomic number. They're all going to have the same number of proteins. Okay, so if we go back here to carbon, every carbon isotope is going to have an atomic number of 6. Okay, so they're all going to have 6 protons. But whereas the standard is an atomic mass of 12, we can have carbon-13, we can have carbon-14. Okay? And so since neutrons and protons have the same mass, the way to figure out how many neutrons they are is you're just going to take the mass and subtract the atomic number from, just like we did on the previous slide. So let's walk through it for hydrogen isotopes. So in hydrogen, we have what's called protium, which has an atomic number of 1 and atomic mass of 1. And so if you subtract 1 from 1, that tells you that there's 1 proton because that's the atomic number. But because the mass is only 1, that means this one has no neutrons. Now, hydrogen with an atomic number of 2 is called deuterium. Deut being a prefix meaning 2. And so in this case, if we subtract the mass from the number, we have 2 minus 1. So this tells us that this isotope of hydrogen has 1 proton and 1 neutron. And then there is a third hydrogen isotope we could talk about, and that's tritium. And this one has an atomic number of 3. So how many protons and how many neutrons is this one going to have? That's right. It's still only going to have 1 proton, but it's going to have 2 neutrons. Okay. So when you look at the 3 different hydrogen isotopes, you can see the first one with a mass of 1 only has a proton. The second one with a mass of 2 has a proton and has an electron. The second one has 1 proton and 1 neutron to bring its mass up to 2, and it still has the 1 electron. And then the third one has 1 proton and 2 neutrons to bring the mass up to 3, and it still only has 1 electron. Okay. So with 1 proton and 1 electron, this is neutrally charged. This one's neutrally charged, and that one's neutrally charged. The charge hasn't changed. The only thing that has changed is the number of neutrons. So that's the only thing that changes in an isotope, the number of neutrons, which then changes the atomic mass. All right. So here's something for you to do. I've given you 2 different isotopes of carbon, and down here at the bottom, there are 3 isotopes of carbon. So do these 2 first. And carbon with a mass of 12, how many protons, how many neutrons, how many electrons? And then on the right with a mass of 13, how many protons, how many neutrons, how many electrons? And then if you get to that one, switch to carbon 14, because it's this carbon 14 that we use for our dating. And that's because what we know is carbon decays over time. And so that's how we do it. So please stop this, figure this out, check with me, check with your peers, make sure you're doing it right. And then I will see you back when we hit our next topic. So thank you for all your hard work, and make sure you understand this chemistry and bring it back to the forefront so we can use it this semester. Thank you.